Bismillah ar-Rahman ar-Rahim. Today, inshallah, we're going to talk about race conditions in parallel programming. So, what is exactly race condition? Race condition occurs when multiple threads try to access and modify shared data at the same time, leading to unpredictable results. Here's an example of race condition. As you can see here, at the parallel region, x and pi are shared variables, which indicates that multiple threads can update those variables at the same time, which may lead to conflict or unpredictable results. So, how can we solve this problem? In OpenMP, we have three solutions to this problem: critical, atomic, and reduction. First, we're going to talk about critical. So, critical section ensures that only one thread at a time can execute the enclosed code. The entire code block following the critical directive is executed by only one thread at a time, ensuring thread-safe execution. While effective for ensuring correctness, using pragma-1p critical can introduce significant overhead due to thread contention, especially if the block is frequently accessed by multiple threads. Ideal when you need to protect a large block of code that involves more than just a simple memory update. Here is an example of the critical section. You can write pragma1p critical and then write the code that you want to protect.
Now with the second solution, atomic update. This method ensures thread-safe operation on a shared variable by locking the variable during a single memory update. This prevents race condition without locking the entire block of code. This method is suitable for simple operation like addition and subtraction, but it's not ideal for complex operation or scenarios involving multiple shared variables. Here an example of a code that we used atomic update with. As you can see, we added a code line pragma omp atomic before the pi increment. This will prevent multiple threads to update the value, which could lead to misleading or incorrect answer. Here is a comparison between the critical and atomic solutions to understand when to use each of them. The scope of critical is an entire block of code, while the atomic only applies to the memory update. The execution behavior is the critical ensure that the enclosed code block is executed by only one thread at a time, while the atomic ensure atomically for the specific memory update. Of course, the critical have a higher overhead than the atomic because it locks a larger code segment. The lock type for the critical is a lock code segment, while the atomic is lock data variable. When to use the critical is when you have a general purpose synchronization for any critical section of code. When you want this block of code to be executed only by one thread, then the critical is the best choice. But for atomic, if you have just a simple atomic operation like an increment in a shared variable, and you want to ensure that the result will be correct, then using atomic will be the best choice.
Hello, my name is Amal El-Wahabi and I'll walk you through the reduction method. Reduction is a parallel computing technique designed to efficiently aggregate values like summing numbers or finding a maximum. It is particularly useful in scenarios where large datasets or complex complications need to be processed quickly. Here is how reduction works. Each thread independently computes partial results for a shared task. At the end of the parallel section, these partial results are combined using an operation like addition or multiplication into a single final result. This approach not only speeds up the computation, but also ensures consistency by preventing race conditions. Some advantages of reduction that it significantly reduces execution time by making full use of multiple threads. And additionally, it ensures consistent results by avoiding race conditions. And finally, it is highly suitable for handling large datasets and performing complex calculations efficiently. Here is an example of reduction. In this code snippet, we calculate the sum of an array using parallel threads. Each thread calculates a partial sum, and the reduction clause ensures that the partial sums are combined into a final accurate result. Now let's compare reduction with other methods. Critical section is suitable for general-purpose thread synchronization, locking a block of code to ensure one thread execution at a time. Atomic method is ideal for lightweight updates to a single variables, providing faster synchronization than critical section. And finally, reduction, which is the best choice for tasks that involve aggregation and computation over large datasets. Thank you for watching.